In this video, we're going to take a look at section 4.3 on complements and conditional probability. Now, we've talked about complements in the previous videos, but we're going to be looking at one special type of complement in this section, which is the probability of having at least one of something occur. And the complement of having at least one is to have none at all. So at least one means one or more. One or two or three or four, however many are possible. The opposite of having at least one is to have none at all. And so the complement rule for that would be that the probability of at least one equals 1 minus the probability that none occur, or that you get none of that thing. And this is a really handy way of calculating it, because if you try to calculate it directly, the probability of at least one, you have to actually find the probability of getting exactly one, the probability of getting two, the probability of getting three, and you have to add up all those probabilities in order to calculate it that way. Whereas if you use the complement, you do 1 minus the probability of getting none, and that's just one calculation. So it's usually a lot easier to calculate if you use the complement. All right. For conditional probability, this is another one we have discussed. You can calculate it in this way. Finding the probability that B occurs given that A has occurred can be calculated by taking the probability that both A and B occur divided by the probability that A has occurred. The conditional probability of B given A can be found by assuming that event A has occurred, and then calculating the probability that event B will occur. And we've practiced doing that in the previous section. And so we'll see a couple more problems like that. I don't normally use the formula that you see on the screen to do that calculation. I usually do it the way we were doing the previous problems in the last section without this formula. So let's just take a look at some of the examples that you might come across in the section. Determine the written description of the complement of the given event, then find the probability of the complement. When a couple has 5 children, the event that all 5 are girls. That's the event that's being described. We want to find the complement of that event. And this is not at least one and none. That's not what's going on here for this particular example anyways. So what is the complement of all 5 are girls? Now, if you're thinking, oh, it's that none of them are girls, that's sort of an opposite, right? That's the other extreme. So having with 5 children, all 5 of them being girls is one extreme. None of them being girls is the other extreme. So in a way, they're kind of opposite. But what we mean by complement is not necessarily the exact opposite of it, but all the ways in which that thing does not happen. That's the kind of opposite we're talking about. So the event of all 5 children being girls, what are all the ways that that does not happen? Well, having no girls is one way for them to not all be girls, but you could also have 4 girls and 1 boy, right? That's also not having all 5 girls. And so that would be part of the complement as well. Also, 3 girls and 2 boys would be another way of not all 5 being girls. So the complement is going to be 4 or less girls. That's all the ways in which you do not have all 5 being girls, is to have either 4 or less girls out of the 5 children. All right, so be careful not to just go to the other extreme as your complement. You want to take all the other possible events in which that particular description does not occur. 4 girls and 1 boy would be one way of not having all 5 be girls. I'm just repeating myself, so I won't go through that again. So this would be the complement. Now let's calculate the probability of that occurring, right? So we want to find the probability that we have 4 or less girls out of 5 children. Now that's a lot of things to consider, right? You have to consider the probability of having 4 girls out of 5 children. You have to consider the probability of having 3, 2, 1, right? So 4 or less means 0, 1, 2, 3, or 4 girls. So you have to calculate those 5 different probabilities and add them together. Now these are mutually exclusive. They can't happen at the same time, right? You can't have both 1 and 2 girls out of 5 at the same time. So you don't have to worry about overlap or double counting, but it would still be 5 separate calculations and then having to add those 5 together to get the probability of having 4 or less girls. You'd have to do this, right? It'd be the probability of 0 girls plus the probability of 1 girl plus the probability of 2 plus the probability of 3 plus the probability of 4, right? That's how you would, because it's an OR, right? It's the addition rule. The alternative way of calculating that would be to use the complement, right? That this will equal 1 minus the probability that all 5 are girls. And that way you're only having to calculate one probability, that all 5 of them are girls, and then take 1 minus that to get the probability that there are 4 or less girls. So what is the probability that out of 5 children, all 5 of them are girls? We want to use the multiplication rule for this, right? Because we want to find the probability that the first child is a girl, and the second child is a girl, and the third child is a girl. You get the idea. And the fifth child is a girl. And so this is going to be multiplication. Probability that the first child is a girl times the probability that the second child is a girl, 5 times. All right. And so we're going to have, what is the probability of the first child being a girl? Well, assuming genders are equally likely, it's a 1 in 2 chance, right? 1 in 2 chance that the first child will be a girl times 1 in 2 chance for the second child to be a girl, 1 in 2 for all of them, because these are independent events, right? So the probability that the second child is a girl is not affected by the gender of the first child. So it's not more or less likely for the second child to be a girl, given that the first child is a girl. Now, that's what we're going to assume. I've actually heard anecdotes to the opposite effect of that when your first child is a girl, you're more likely to have girls after that. But I don't know if that's true or not, but I've heard that before. All right. But we're just going to assume that they're independent. That every time you have a child, it's 50-50 boy or girl, even though that may not be always necessarily true. And we have 5 children, so we want to multiply 1/2 to itself 5 times. So because it's the same number over and over and over, we can just use an exponent. So it's going to be 1/2 to the 5th power. And I just did a video for a different class. Oh, it's in my pocket. And I had my cell phone handy because I had to do some calculations, and then I couldn't find it, but it was in my pocket. Okay, so we have 1 divided by 2, which is 0.5. And we want to raise that to the 5th power. And so you get let's do it like this. Whoops. Help if I held my pen the right way. 0.03125. That's the probability that out of 5 children that all 5 of them would be girls. Right? There's a 1/2 probability that the first child is a girl, 1/2 probability that the second child is a girl, so on and so forth for all 5 children. And because it's an and, because we need the first child to be a girl and the second child to be a girl and the third child to be a girl, that it's a multiplication rule. So we multiply 1/2 to itself 5 times. We get this. That's the probability that all 5 are girls, but I want to find the probability that there are 4 or less girls. So I want the complement of this, which means I want to take 1 minus that probability to find the probability that there are 4 or less girls out of 5 children. And so I'm going to take this 1 minus that number, and we get 0.96875. And then again, round appropriately, whatever the directions might say on the homework. But I'm just going to leave it exact. That's the exact value. So if you have 5 children, there is a 97% chance that you'll have 4 or less girls. Or in other words, there's a 97% chance that they won't all 5 be girls. Right? Okay. Determine the written description of the complement of the given event, then find the probability of the complement. So same as the last problem. When 4 digits between 0 and 9 inclusive are randomly selected with replacement for a lottery ticket, at least one of the digits is 0. Right. So this is using the formula that we talked about at the beginning, right? at least 1. The complement of at least 1, I can't spell, at least 1 is none at all. Right? So the complement of at least 1 is to have none. So the complement of having at least one of the digits be 0 is to have none of the digits be 0. All right. And so we want to find the probability of that complement. So I want to find the probability that if I'm selecting 4 digits at random with replacement, meaning I can repeat the same number. So for example, I could get 2, 3, 3, 3. I can have the same number multiple times in this selection. Right. What is the probability that none of the digits selected will be 0? I don't want to use the complement to calculate this, because the complement would be to take 1 minus the probability that at least one of the digits is 0. And then we have to find the probability that you have the probability that you have 1 0 plus the probability that you have 2 zeros plus the probability that you have 3 zeros. And it's going to be a very difficult calculation to do. It'll be easier just to directly calculate what's the probability that none of my 4 digits are 0. And that means the first digit is not 0. And the second digit is not 0. And the third digit is not 0. And the fourth digit is not 0. And these are ands, right? I need that particular sequence of events to be the case, to have no zeros in my selection, in my number that I'm using for the lottery. And so it's multiplication rule. It's an and. It's the multiplication rule, right? So I'm going to multiply the probability that the first number is not 0 times the probability that the second number is not 0 times the probability that the third number is not 0 times the probability that the last number is not 0. And that's how we will know that we have no zeros in our 4-digit lottery submission. All right. Now, if I'm picking numbers at random, what's the probability that when I pick that first number, it will not be 0? Well, how many ways can I choose a number that's not 0? There are 9 digits to choose from, 1 through 9, right? That are not 0 out of, and this is a little bit tricky, out of 10 digits that I could pick altogether. You might say, 10, what do you mean? We're picking between 0 and 9, but 1 through 9 is 9 digits, and then when you add 0 to that list, that's 10 altogether. So there are 10 single digits that you have to choose from, 9 of which are not 0. So the probability of getting a non-zero digit when you randomly pick that first number is 9 out of 10. Now when I go to pick the second number, because it's with replacement, because I can choose the same number twice, I'm back to having 10 numbers to choose from. And out of those 10 numbers, 9 of them are not 0. And so again, these are independent events. Picking a non-zero digit for the first digit does not affect the probability of getting a non-zero digit for the second one, because we can still choose from the same number of digits. There's still 10 to choose from. There's still 9 that are not 0. And that continues to be the case for the other digits. And so we'll have 9 out of 10 multiplied to itself 4 times. So the quick way to calculate that would be to take 9 tenths to the 4th power. And so I'll take 9 divided by 10, which is 0.9. I'll just type in 0.9. Raised to the power of 4. And that did not give me, I got 13.7. I don't know how I got that. But obviously that cannot be the right answer, because probabilities can't be more than 1. So it's important to realize, like, if you type something wrong into your calculator, it's good to be able to recognize, hey, that answer does not make sense. I must have did something wrong. So let me try again. 0.9 raised to the power of 4. Okay, this is more sensible. I don't know where I got 13.7 from. 0.6561. All right. So you have a 66% chance when you pick 4 digits at random that none of them will be 0. And you didn't have to use complements to calculate that. So this is a good exercise in realizing when to use the complement and when not to use it. So you want to try to minimize the number of probabilities you have to calculate, and that's, you use a complement when the complement has less things to calculate than the event you're worried about itself, right? I don't know if that made sense what I just said, but if the event you're trying to calculate the probability for has more probabilities to calculate than the complement, then you should just use the complement and do 1 minus that to get the probability that you're trying to find. Okay. A certain model of alarm clock has a 99% chance of working on any given morning. I felt like there was one other example I was supposed to have here, but I guess it's not there. So either it got deleted or I decided to leave it out. Has a 99% chance of working on any given morning. So you have an alarm clock. Most of us use a cell phone. I mean, I don't know that to be true, honestly, but I assume most people use a cell phone as their alarm clock. But let's say you splurge and you buy an alarm clock separate from your phone. And that's what you use to wake up in the morning. And let's say it's been quality tested and it's assured to work 99% of the time. What is the probability that with one of these alarm clocks, it does not work and you oversleep and you get in trouble at your job or school because of that? So here we would use a complement because we're given the probability that it does work, right? So the probability that the alarm clock works is 99%, which is 0.99 as a decimal. I want to find the probability that it does not work. I'm trying to think of the easiest way to write it without having to write as much. I'm trying to write it with the minimum amount of words possible. Probability that it does not work is 1 minus the probability that it does work. So I use a complement not because it's less probabilities to calculate, but because the probability I'm being asked to find, I don't have. I don't have numbers to calculate it either. But the complement is a probability that I do have, right? So the complement is the probability that it does work, and that's given in the problem. So I'm using it because of the information I was provided. So it'll be 1 minus 0.99, which is going to be 0.01. So 1% chance. So if you buy one of these alarm clocks, there is a 1% chance on any given morning that it does not work and you oversleep because of it. Now, what engineers will do, now this is maybe not an engineering situation necessarily, but in many systems, there are fail-safes, there are redundancies for the purpose of if you're uncomfortable with that fail rate, right? That's a 1% fail rate. That might be a little too high. You don't want to take that chance, right? You got an important job. You can't oversleep anymore, right? And 1%, maybe even though that's rare, it might still be a little too high for your comfort level. And you want to make sure that you are not going to oversleep. And so maybe instead of just using one alarm clock, you could use 2 of them, because the chance of both of them failing on the same morning should be astronomically low, right? And we can actually calculate it. In fact, that's what we're going to do, right? So you build in this redundancy of having a second alarm clock that also has a 99% chance of working on any given morning. What is the probability that with 2 of these alarm clocks, at least one of them works, right? Because as long as at least one of them works, you won't oversleep. You don't need both of them to work, just at least one of them needs to work, right? And that way you're not oversleeping, right? So what's the probability that at least one of the alarm clocks is going to work? Well, if we try to calculate that directly, that means we have to calculate the probability that one of them is working and the probability that 2 of them are working, right? Because that's at least one. At least one means either one of the alarm clocks worked or both of them worked. It's an or, right? Either one worked or 2 worked. But also we have to take into account the probability that, we can't have both 1 and 2 work at the same time. But either way, I don't know what I was thinking. It's still 2 calculations that you'd have to do, right? And I don't know. I feel like there's some hidden difficulty that might be there that I'm not even thinking about right now. The point I'm trying to make is it'll be easier to calculate this probability using the complement, right? And the complement of having at least one alarm clock work is having none of the alarm clocks work, because this is the rule that we talked about at the beginning of the video. The probability of at least one is 1 minus the probability of none, right? And what is the probability that none of the alarm clocks work? Right. This means that the first alarm clock does not work. Oops, that's kind of hard to read. Does not work. And the second alarm clock does not work. All right. And so it's a multiplication rule again, right? Because we need and for none of them to work, we need the first alarm clock to not work and the second alarm clock to not work. It's not really a sequence of events because we assume the alarm clocks are supposed to work at the same time, but you can kind of think of it as a sequence. It's alarm clock A fails and then alarm clock B also fails, right? It's a multiplication rule. So we're going to multiply the probability that the first alarm clock, I feel like I'm saying that so many times I'm having trouble repeating it, and that the second alarm clock does not work. And I don't know what I'm saying there. We want to multiply, right? So it's the probability that the first alarm clock does not work times the probability that the second alarm clock does not work. Now, there's another thing we might consider here is, are these events independent? Well, if they're plugged into the wall, no, the alarm clocks maybe functioning or not would not be independent if they're plugged into the walls. Because the walls, I don't know why I'm saying plural there, but if both alarm clocks are plugged into the wall, if your power goes out, they'll both fail. So I guess we should assume that these alarm clocks are battery driven so that they are independent of each other. They're not using the same power source. And that way we can do this calculation. Because you wouldn't want to use two alarm clocks that are both plugged into the wall if you're worried about your power going out as being a reason why both of your alarm clocks fail, right? You want to make sure they're independent of each other so that when one fails, it doesn't cause the other one to automatically fail, right? So if we're being smart about this, if we're being engineers about it, we're trying to build in this redundancy to make sure that we don't oversleep. We want those redundant systems to be independent, because if they're dependent on each other, when one fails, it might be more likely for the other one to fail. And then what's the point of having that redundancy, right? So let's have them be independent of each other. Now, what's the probability that the first alarm clock does not work? That's what we just did on the last screen. It's 0.01, right? There's a 1% chance that it fails. What's the probability that the second alarm clock also does not work? It's also a 1% chance. And we're going to multiply these together. So it's going to be 0.01 to the second power. And this is the probability that none of the alarm clocks work. All right, I should know what this is. I'm pretty sure it's 0.0001. All right, so there is a 0.0001 probability that both alarm clocks fail on the same morning. That's 0.01%. It's really rare for both alarm clocks to fail at the same time. So 1 minus that would give me the probability that at least one of the alarm clocks is going to work on any given morning. And so that's 0.9999. So you have a 99.9% chance that we will not oversleep, that the alarm clocks are going to wake us up. All right. What if that's still not good enough for you? You have a really important, like you're in charge of like the nuclear arsenal, and you have to, maybe we should think of it like this, like, have you seen the show Lost? You have to press the button in the hatch. I don't know if you've seen the show. I recommend watching it. It's got its flaws, but it's still a pretty interesting show. And there's a guy in there named Desmond, and he's stuck in this hatch. And every 98 minutes, I can't remember, is it 98? Can't remember. But every so often, he has to press this button on the computer or something bad happens. And so what if that's you and you cannot oversleep because if you don't press that button, a plane is going to crash, which is what happens on Lost, right? Maybe 99.99% chance is not enough of an assurance for you. And you have to be very, very certain that you do not miss pushing this button. So you buy 5 of these alarm clocks. Now, if you're stuck on an island somewhere, you can't buy alarm clocks, but you rig up 5 independent alarm clocks that each have a 99% chance of working. What is the probability with 5 of these alarm clocks that at least one of them works? Right. So probability of at least one alarm clock working out of the 5 is going to equal 1 minus the probability that none of the alarm clocks work. Now I want to save myself some writing here, which is adding to the runtime of this video. It's the same idea as before. The probability that none of them work is the probability that the first one doesn't work, and then the second one doesn't work, and then the third one doesn't work. It's multiplication rule, and we're going to multiply them together 0.01 5 times. Right? Now, there's 5 alarm clocks. Each one individually has a 1% chance of failing. So the probability that all 5 of them fail is going to be 0.01 multiplied to itself 5 times. So it's going to be 0.01 to the 5th power. Now this one I think I'll just go ahead and use my calculator on. I think I should be able to figure it out. But let's just double check it. So 0.01 raised to the 5th power is going to be how many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So it's going to be 0.1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, and then we hit 1. All right. So that's the probability that all 5 alarm clocks would fail on the same morning. There's still a chance. There's no way to get out of it. If each alarm clock has a 99% chance of success and a 1% chance of failing, then there's always going to be some chance that all of them would fail on the same morning. But we can really, really reduce that chance to nearly 0. In fact, this small of a number is practically 0. It's not exactly 0. Can it happen? Yes. But it's so phenomenally rare. It's such a small probability that it's practically 0. So that's another concept in, statistics and probability. When a probability is so vanishingly small, you can treat it as if it were 0, as if it were impossible, even though technically it's not impossible. Right? Because remember, a probability of 0 is impossible. Right? It's not impossible for all 5 alarm clocks to fail here, but it's such a small probability that it's practically impossible. Right? So what's the probability that at least one of the alarm clocks will work for you? So you don't miss pushing the button. It's going to be 0.999999. I think 10 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So 99.999999% chance that at least one of your alarm clocks will work. Okay. So that's how that concept works. Now, this is something I brought up in the previous video, but that previous video became longer than I expected because it joined 2 different lessons together into a single section, and so I didn't want to add this into that lesson. Plus, this material actually fits better with what we're talking about in this section. What is the probability that in a room of 30 people, at least one person, so there's the at least one person has the same birthday as you, as your birthday? So you're not counting you as one of the 30 people. So you're in a room with 30 other people. What is the probability that at least one of those 30 other people in the room would have the same birthday that you have? So you can calculate it in the same way as we did with the alarm clock example. So this question, the first question here, is no different than the alarm clock example. The probability that at least one person in the room has the same birthday that you have is 1 minus the probability that none of the people in that room have the same birthday as you. Right? Because again, if you're going to do the probability that at least one person has the same birthday as you have to calculate the probability that one person has the same birthday, and 2 people have the same birthday as you, and 3 people have the same birthday as you, up to 30. Because it's crazy. It's practically 0. It's practically impossible. But there is a chance that all 30 people in that room have the same birthday that you have. Right? Now, even having 3 people out of 30 with the same birthday as you is going to be really, really small. But if you want to calculate that probability precisely, you'd have to consider the probability of one person having the same birthday as you, and then 2 people, and then 3 people, all the way up to 30 people. I don't want to do 30 different probability calculations. It'll be easier to do the complement. And I'll just find the probability that nobody in the room has the same birthday as me, and then take 1 minus that to get the probability that at least one person would have the same birthday as me. Now, what is the probability that one person does not have the same birthday as you, right? We want to find the probability that nobody has the same birthday as you. What is the probability if I pick a person at random that they would not have the same birthday that you have? Well, there's 364 other days they could be born on. Having trouble talking. There's 364 days, other days, that they could be born on that would not be the day that you were born on. Right? So there's 364 ways for them to not have the same birthday as you out of 365. And I think the reason I kind of got caught up on my words is because while I'm saying, explaining, thinking, talking, I'm thinking about other things sometimes. And what was kind of in my head was, okay, yes, there's leap year, there's leap day, which we're just not going to include in the calculation. That'd be really hard to manage, I feel like. Maybe not. You could just say, well, there's 366 days altogether, because there's the 365 normal days that we have every year, and then there's the one leap day that we have every fourth year, and then trying to figure that into the probability, we don't want to get into that little minute detail that is not going to affect the probabilities all that much. So for one person, the probability that one person does not have the same birthday that you have is 364 out of 365. Right? There's 364 ways for them to not have the same birthday as you out of 365 days they could have been born on altogether. All right. Now that's for one person. We have to do this for 30 people. So what's the probability that the second person does not have the same birthday as you? Also 364 out of 365. And that's independent, right? Whether the second person has the same birthday as you, that probability does not depend on the outcome of the first person having the same birthday as you. And so these are independent events, thankfully, which means we're going to get this fraction how many times, right? That's the first person, that's the second person. We have to do this 30 times because there's 30 people in the room that we're checking against. All right, so 30 times. I'm not going to write it out 30 times. But this would be the probability that nobody in the room has the same birthday as you. It's the probability that the first person doesn't have the same birthday as you, and then the second person doesn't have the same birthday as you, and then the third person doesn't have the same birthday as you. So on and so forth until you reach the 30th person not having the same birthday as you. And you want to multiply all those probabilities together. Because it's the same fraction, 30 times, we could just take 364 over 365 raised to the 30th power. All right, so let's see if my calculator can handle that calculation. All right, so we're going to have 364 divided by 365, which is really close to 1. It's 0.9972. So you might think, oh, that's so close to 1 when I raise it to the 30th power. I don't know what I'm saying. When I take a number that's close to 1 and raise it to the 30th power, you might think it's not going to change it that much. But with a high enough power, it doesn't stay close to 1 like you might expect. If that's something you might be expecting, I don't know. Raised to the 30th power, it's still pretty close though. It's a 0.92099. I'll just kind of stop there. All right. So this is a 30 here also. I'm really unhappy with how I draw my 3's on here. Okay, let's erase that and draw it again. 30, okay. And that's the probability that no one out of the 30 people will have the same birthday as you. To find the probability that at least one of them does, you take 1 minus that. All right, so we're going to do 1 minus that number, and we get a pretty small probability actually. All right, so you're going to get 0.079008. That's what I get. So I'll just kind of round. This seems like a good place to round it at. So it'll be about 0.079. What am I saying? Why did I put a point there? 79. Right. Which what I was about to say is that's 7.9%. So there's about an 8% chance. If you go to a room full of 30 random people, there's about an 8% chance that somebody in that room would have the same birthday as you. That is not the same question as asking, what is the probability that in a room of 30 people, that 2 of them have a birthday in common? Not have the same birthday as one person in particular, but just that any 2 people might share a birthday in common. All right, so think about the difference there, because if I'm asking, what's the probability that in a room of 30 people that somebody has the same birthday as you were born on a particular day. And I'm asking, what's the probability that one of those 30 people, at least one of them, was born on that same day? So I'm picking the day and checking to see what's the probability that of these 30 people, at least one of them was born on that same day. Whereas the second question is not picking the day. It's just saying in a room of 30 people, what's the probability that 2 of them would have a birthday in common? But I'm not specifying what day that birthday has to be. And so it's a completely different question. And the reason this is called a birthday paradox is because the answer to this second question is surprising. A lot of people are really shocked and almost in disbelief at this probability. So let's go ahead and calculate it though. So what's the probability that at least 2 people share a birthday in a room of 30? Now, again, trying to calculate that directly would be hard to do, but we can do complements. It's going to be 1 minus the probability that no two people in that room share a birthday. All right. Now, in order to calculate, this calculation is a little bit trickier to do. So we have to look at the probability that the first person does not, how do I want to word this? Does not share a birthday. Let's put it that way. Does not share. Let's just put does not share, just to keep it simple. What I mean by that is, what's the probability that the first person we pick does not share a birthday with anybody that we've previously chosen? Now, for the first person to not have the same birthday as anybody that came before him or her, that probability is 1. There's no way, because they're the first person. There are no birthdays that they can share with the people that came before them because nobody's come before them. Right? So the first person, the probability that they do not share a birthday with somebody else that we've already looked at is 1. It's 100%. They cannot share a birthday with anybody else. Then we go to choose the second person from that room. What's the probability that they do not share a birthday with the people that came before them? So we're kind of doing like a conveyor belt thing. We have 30 people in the room. We will have them exit the room one at a time. And we will check their birthday as they leave the room. So the first person that comes out of the room, we're going to say, what's your birthday? And we're going to look in our list to make sure that they don't share a birthday in common with somebody that already left the room. The first person that leaves the room, there's no birthdays on our list. So we will write their birthday down. There's no way they would share a birthday in common with somebody else that left the room already because they're the first person to leave. So that's why it's 100%. There's no way that they would have a birthday in common. It's certain to be the case they will not share a birthday with somebody else who has already left the room since they're the first ones to leave. For the second person, we say, okay, what's your birthday? What's the chance that they have a birthday in common with the person that already left? Right? Or actually, I should ask, what's the probability that they do not share a birthday in common with the person that already left? Well, there are 364 other days they could have been born on other than the one that's currently on my list, right? Because one person's already left. I have one birthday on my list. What's the chance that the second person leaving does not share that birthday? It's 364 out of 365. Right? There's 364 other days that they could be born on out of 365 days altogether. Right? So for the second person to not share a birthday with the people that left the room already, there's one birthday already on my list. There's 364 other days they can be born on that would not share a birthday with the birthday that's already on my list. I don't know. I feel like I'm not saying it perfectly, but hopefully you get the idea. Now, 2 people have left the room. I have 2 birthdays on my list, presumably 2 different birthdays. So when the third person goes to leave the room, I'm just thinking now about the calculation I have to do, and I don't know if I can do it. It'll take me a while. I'm going to have to pause the video. So when the third person goes to leave the room, we want to know what's the probability that the third person that's leaving does not share a birthday in common with the 2 people that have already left. Right? So for the third person, what's the probability that they do not share a birthday with the people that have already left? There's 2 people that have already left. So for them to have a different birthday than the 2 people that have already left, how many days are available that would be different from the 2 days I have currently on my list? There are 363 other days for them to be born on than the 2 that are currently on my list from the 2 people that have already left, out of 365. So you get a sense of what the pattern's going to be here. For the fourth person, there are 362 days remaining that they could be born on that would not share a birthday with anybody currently on my list, out of 365. Right. So this is the first person, this is the second person, this is the third person, this is the fourth person. Right. We need to go all the way to the 30th person. Right? Now, I don't want to have to write out every single fraction, but the problem here is that these are not independent events, right? The probability that the nth person does not share a birthday in common with the previous people is going to change based on how many people have already left, right? And so for the 5th person, it'll be 361 out of 365, for example, because there are only now 361 days remaining for them to have a birthday on that is not the same as one of the birthdays I already have on my list, right? So the math here is that if you think about it, there's 365 days altogether. The fifth person has 361 days remaining that they could be born on that would not be the same as one of the days that have already been, recorded. 361. They're the fifth person. So what I'm doing there is I'm subtracting 4, right? 365 minus 4 gives me the 361. So the fifth person has 4 days removed from what's available. How do I say? There's 4 days that they can't be born on in order for them to not share a birthday. So the fifth person has 4 days unavailable to them to be born on if they want to make sure to not share a birthday in common with somebody else. So what about for the 30th person? What would I want to do? I want to take 365 minus the 30th person would have 29 days unavailable to them to be born on in order for them to not share a birthday in common with somebody else that's already left the room. So 365 minus 29. It's going to be 336. So this last person, the probability that they would not share a birthday in common with the previous people that have left the room is going to be 336, because that's how many days are still available that would not match one of the dates on my list that I'm keeping out of 365. I hope that makes sense, right? Right, because 29 people have already left the room. Those 29 people each have a different birthday. And if I want the 30th person to not share a birthday in common with those 29 people, there's only 336 days available for them to be born on that would not be shared in common with the 29 people that have already left. All right. Hopefully that makes sense. That's the best I'm going to be able to do, I feel like, at this point. All right. And I have to multiply these together. All right. So I'm going to pause this because what's going to have to happen is I have to multiply 29 or 30 different fractions together. It's going to take me a while to do. So I'm going to go ahead and pause it and figure it out. Okay, well, that took quite a while for me to calculate, and I actually started on my cell phone. It's an iPhone, and I got to pretty close to the end, and then I typed something wrong, and it was so frustrating. So then I went to Google and brought up the Google calculator, and I had to get a little creative with how I typed it in, because like typing in each fraction at once, so tedious, and you make one little mistake and you just have to start over again, and that's really frustrating. So I got this result, which at first I almost didn't trust, but actually I kind of confirmed it by looking it up, and it seems to be on the right track. So I'm getting 0.29, let's just go with 0.294, right? So we'll round it to the third decimal place. 0.294 for the result of multiplying all these fractions together, right? So let me use a different color here. 0.294. Now, that's the probability in a room of 30 people that none of them share a birthday in common. None of the 30 people share a birthday in common with anybody else in that room. We were looking for the probability that at least 2 people in that room would share a birthday in common. So we want the complement of this. So we take 1 minus that to get the result of... Well, I should be able to. I feel like my brain is fried at this point. This is my second video for today, and after trying to do that last calculation, I think I'm down for the count. Minus 0.294, so it's going to be let's do this, 0.706, which is about 70%. I was going to say, I should round it up to 71%, but whatever. Still shocking. Right? A 70% chance that in a room of 30 people, 30 randomly selected people, there's a 70% chance that 2 people in that room, at least 2 people in that room, will have a birthday in common, which is shocking. It doesn't seem like it should be that high for such a low number, because especially when you think about the probability in a room of 30 people that they share your birthday is only 8%, right? But for there to be a chance that at least 2 people in that room would share some birthday in common is a 70% chance. It turns out, and this is kind of what I thought I was going to calculate, but that's why I didn't trust my result at first, that you would need 23 people in a room for there to be a 50% chance that 2 of them would share a birthday in common, at least 2 of them. And that just seems like a really high probability for such a small number of people. But the math bears that out, and that's why it's called the birthday paradox. there's nothing paradoxical about it. There's no contradictory logic or circular logic or anything like that. It's just a highly counterintuitive result. So people call it a paradox because you almost can't believe it, even though the numbers show you that it's the case, that it's true. All right. And so you could try this out sometime. Maybe if you're at a party. Now, there's a 30% chance it doesn't work. But if you're at a party with like 30 people, check to see what everybody's birthday is. You don't have to ask the year. You can just ask for the month and day. And in a room of 30 people at a party, there should be a 70% chance that 2 of them would have the same birthday. So it's kind of an interesting party fact. But I'm sure with my luck, if I tried to like impress people with that and I started asking for birthdays, I'd be in one of the 30% birthday party groups where nobody has a birthday in common. So there is that chance of it backfiring. So, all right. So I apologize for how long that took, but it's just the birthday paradox is a pretty famous math problem. And it was really appropriate given the material that we're covering to talk about it. And I just think it's really interesting. So I just wanted to share that with you guys. All right. So back to our polygraph test that we've seen throughout chapter 4. Here's that chart again. So we have a few more questions and we'll be done with this video. So it's not too much longer. Find the probability that, let's see, how much more is it? Okay, 2 more. 2 more. In fact, the last page is not even a problem. It's just an anecdote. Find the probability that the subject did not lie given the subject had a positive test result. So we're picking one person. What is the probability that we pick a person who did not lie, assuming that the person we choose has a positive test result? We actually did a problem very similar to these problems actually, in a previous video. I can't remember if it was in 4.1 or 4.2. But the idea I came up with during that video was to think of it this way, that you have sent home everybody else except for the people that have a positive test result, right? So remember, there's 98 people altogether in this study. You sent home the people that had a negative test result. You just said, you're done. We don't need you around anymore for this study. You're free to go home. Only the people that have a positive test result you kept. And given that you're keeping just the people with a positive test result, what is the probability out of that subgroup that you would pick a person that did not lie? So that is the probability we're being asked to calculate. So you can really think of it in those terms. You've sent home everybody else. You've only kept the people that had a positive test result. And now you want to calculate this probability that out of that subgroup, you choose somebody that did not lie. So this is a conditional probability. So you want to find the probability that you pick somebody that did not lie, given that they had a positive test result. So you're only considering the people with a positive test result when you do this probability. So of the people that had a positive test result, how many people are there to choose from? These are the people that had positive test results. There are 57 of them, right? So there's 57 people now left in the study. You sent home everybody else. You only kept these 57 people for further questioning, right? So there's only 57 people to choose from now. That's your denominator. Of those 57 people, how many did not lie? How many people did not lie? Only 15 of those 57 people did not lie. So the probability of choosing somebody that did not lie out of just the people that had a positive test result is 15 out of 57. Right, and so that would be the probability for part A. I don't think we need to do all 3 of these. I feel like it's a little redundant. We did one already earlier in an earlier section. This video is already hitting 50 minutes. Let's just do one more of these because it's going to be really redundant, I feel like. In fact, why don't you pick one to do? So pause the video, either do B or C, and I'll just go ahead and write the answer for both of them. So whichever one you pick, you can check to see if you did it correctly. But just do one. And if you get that one wrong, maybe try to do the other one, see if you can match the answer that you see for the other one. All right. So just give me 1 second. Okay, I apologize. I didn't leave the table on the screen so you could get the numbers you needed, but hopefully you could have rewound the video if you were, trying out the problem yourself. So for part B, you want to find the probability that you choose a person that got a positive test result, given that the person did not lie. So again, you're only keeping the people in the pool that did not lie, and out of those people that did not lie, you want to choose somebody that got a positive test result. So going back to the table, these are the people that did not lie during the study. There's 47 of them altogether. 15 of them got a positive test result. So 15 out of the 47 got a positive test result. So that's the probability of choosing somebody that got a positive result. There's 15 altogether in that group out of the 47 people that did not lie. Right. For this one, you want the probability that somebody lied, choosing somebody who lied, given that they got a negative test result. So for this one, you're keeping only the people that got negative test results. And out of those people, you want to know the probability of choosing somebody who lied. So going back to the table, people that got negative test results, there's 41 altogether. So these are the 41 people that got a negative result. Of those 41 people, 9 of them actually lied. So it'd be 9 out of 41. All right. So the last thing I wanted to talk about, because again, it seems apt given the content of this section. And this is taken from the book Innumeracy by John Allen Paulos. It's a book you can buy. It's a fairly short read. It's been around for a while. I don't know if it's something that has really been taken up as a cause, but it's a little bit, the analogy here for innumeracy is illiteracy. So illiteracy is the inability to read. Innumeracy is the mathematical version of that concept. And so this author, if you read the book, he's concerned about just education in general and being able to teach people to have a good number sense. And so the lack of a good number sense is this concept of innumeracy. And he was worried about the rise of this innumeracy that he was seeing in students. And throughout the book, he has these funny little mathematical anecdotes, is the way I think you say that. And this was one that kind of was related to probability I thought I would share. A man who travels a lot was concerned about the possibility of a bomb on board his plane. He determined the probability of this, found it to be low, but not low enough for him. So now he always travels with a bomb in his suitcase. He reasons that the probability of 2 bombs being on board would be infinitesimal. Infinitesimal, if I could say that word. All right. Now, what is wrong, and this is what the whole book is about, right? There's flawed reasoning here. So this is flawed mathematical reasoning. What is wrong with this person's reasoning? Well, if you consider the probability, so let's have A be the event of, okay, well, let's do this. This man, let's give him a name. Let's call him Bob, right? So Bob travels a lot. He's concerned about there being a bomb on the plane. So he brings a bomb on the plane, reasoning that the chances of there being 2 bombs on the plane would be really, really, really small. Small enough that he could feel comfortable traveling. All right. So let A be the event of someone else bringing a bomb on the plane. All right. And we'll let B be the event of Bob bringing a bomb on the plane. And we want to know what's the probability that these both happen, that both someone else brings a bomb on the plane and then Bob also brings a bomb on the plane, right? So we want to find the probability that A happens and then B happens. This is the multiplication rule again, right? So this will be the probability that A occurs times the probability that B occurs given that A has occurred. Now, we don't know what the probability Bob calculated was of somebody bringing a bomb on the plane, but that is what probability of A is, right? It's the probability that somebody else besides Bob is bringing a bomb on the plane, which is, presumably the probability he was calculating earlier about somebody bringing a bomb on the plane and finding it low but not low enough for him, right? So I don't know what that is, but it's a low probability. But here's the problem. What's the probability that Bob brings a bomb on the plane, given that somebody else has brought a bomb on the plane? Well, these are independent events, right? So we don't have to really consider whether somebody else brought a bomb on the plane or not. The probability that Bob is bringing a bomb on the plane is 1. He's certain to do it. He's decided that it's not a random chance. He is bringing a bomb on the plane every time he flies. So the probability that he brings a bomb on the plane is 1. And so that will get multiplied to the probability of somebody else bringing a bomb on the plane. So that'll be that probability times 1, which doesn't change that probability. it's still the same probability. It's not going to be lower because bombs bring, I'm saying the wrong, I shouldn't use Bob because it sounds too much like bomb, but the probability of there being a bomb on the plane is not going to be lowered by the fact that Bob is bringing a bomb on the plane as well, because he's certain to be doing it. And when you multiply those two probabilities together, it doesn't get lower. It stays the same. So the probability of there being two bombs on the plane, with Bob bringing one of those bombs, is the same as the probability of there being a bomb on the plane to begin with, right? It doesn't, again, the probabilities aren't going to get lowered because Bob has made this choice, because the probability of him bringing a bomb on the plane is 1. And when you multiply by 1, this overall probability does not get lowered. It stays the same, right? Now, if this second probability was less than 1, then when we multiply these two numbers that are less than 1 together, it would lower the probability. But that was the flaw in Bob's reasoning, is if it was two random people randomly bringing a bomb on the plane, that chance of occurring is lower than just one person bringing a bomb on the plane at random. But for Bob to say, I will always travel with a bomb on the plane, that makes the probability 100%. It makes it equal to 1. And if that probability is 1, nothing's getting lowered. The probability is just going to stay the same. And so that's the flaw in his reasoning. So it's a funny anecdote because it's hard to really see immediately what the flaw is in that reasoning. Because yeah, you would think in general, 2 bombs on a plane would be more rare than 1 bomb on a plane, but not when you go about it in this way. So that concludes the video on section 4.3, and that concludes the material on chapter 4. If you're one of my students, we will not be having a test just yet. We're going to also cover chapter 5 first, and then we will have a test after chapter 5. So your next test will be on chapter 4 and chapter 5. So if you're one of my students, I will see you in the next video for section 5.1.